Welcome to another episode of Code for Thought Byte-sized. Lint, the Oxford Dictionary tells us, are short, fine fibers which separate from the surface of cloth or yarn. In computing, however, Lint started its life as a shell command on Unix machines, the aim of which is to trap little mistakes just like cloth processors use traps to capture the fluff. Which brings us right to what this episode is about. Using tools to check your code for all the mistakes and aberrations that are so easily made, so easily overlooked, and so hard to fix once they crept in. I'll be starting with some background on Lint itself before discussing why you should be using static analysis tools. I'd like to take you through the list of all tools available, but quite frankly there are just too many of them. So instead I will focus on static analysis tools for the Python language, just as Steve Crouch and Jeremy Cohen did for the interactive Byte-sized RSE sessions that some of you may have attended. Finally, you will hear how my colleagues and I use linting tools in one of our Python projects right at the end of this episode. In the course of this episode, I will mention quite a few tools and references, but don't worry, you will find the appropriate links in the episode notes, so please take a look. But first, a bit of history. It is Stephen Johnson who gets the credit for creating the Lint tool for the C programming language in the late 1970s. It's probably best to read out the abstract of the paper he's written to give an idea of what Stephen Johnson had in mind, so here it is. Lint, he writes, is a command which examines C source code, detecting a number of bugs and obscurities. Well, quite frankly, when I read this line I think, isn't that exactly what a compiler is supposed to be doing? But let's read a little bit further. It enforces, Stephen continues, the type rules for C more strictly than the C compiler. It may also be used to enforce a number of portability restrictions involved in moving programs between different machines and/or operating systems. Another option detects a number of wasteful or error-prone constructions, which nevertheless are, strictly speaking, legal. So there it is, the difference between Lint and compiler, but to make the distinction between them even clearer, he continues writing, the separation of function between Lint and the C compilers has both historical and practical rationale. The compilers turn C programs into executable files rapidly and efficiently. This is possible in part because the compilers do not do sophisticated checking, especially between separately compiled programs. Lint takes a more global, leisurely view of the program, looking much more carefully at the compatibilities. In short, what Stephen writes is that the Lint tool tries to capture code and coding styles that may cause problems down the line, but are in fact perfectly okay at the point of compiling the program. The leisurely view of Lint, Stephen mentions, may be a nod to the different kind of styles engineers use in their code across applications. Since those heady days of C programming in the Bell laboratories, where Stephen worked at the time, linting and other static analysis tools have come a long way. And as mentioned before, today tools are available for most platforms and languages. Like Python, for instance. Unlike the C programming language, as you know, Python is an interpreted language. So there is no such thing as a compilation warning or an error. On the other hand, you'll most likely develop your Python code in an integrated development environment tool, such as PyCharm or Visual Studio Code. These will flag up syntax errors and warnings. And of course, once you run a Python program with syntactic errors, the Python interpreter will tell you so. In short, the development tools you use and the Python interpreter itself will flag up any syntax or other errors that you may make. So why then should you be using something like Lint? Stephen, in the abstract of his paper, talks about compatibilities. Compatibilities between different programs, machines and operating systems, which is fair enough. But I think there is another level of compatibility, that between engineers. As we continue developing software solutions, we all develop our own preferred way of working and coding. In languages like C, for instance, Some may put the opening and closing curly brackets for blocks of code into separate lines, others include them in the same line. Some prefer lines of code to be only up to 80 characters long, some prefer them to be longer. Then there is the naming convention of variables, classes and functions, of course. And what do we do with trading white space? What to do with indentation? Shall it be 2 characters? Shall it be 4 characters? None of what I just mentioned would cause the problem to fall over or create errors or even warnings. However, imagine that 2 or more engineers, each with their own but very different styles, work together on the same source code. Or you've become responsible for software developed by different engineers before you, which happens quite a lot, and not only in scientific software. You will find, as I have in the past, that reading and being able to understand the code is so much harder if the coding styles are all over the place. As a consequence, it'll take more time and energy to maintain the code and change existing functionality or add new ones. Not to mention that it makes working with it, quite frankly, far less enjoyable. In fact, there is a phrase for code like this: spaghetti code. And while spaghettis are great in a pasta bowl, they really have no place in coding. Stephen Johnson must have thought the same when he created Lint over 40 years ago, which tells you that the problem I just described is anything but new. Luckily, since then a number of tools have sprung up to help you automate enforcing agreed coding styles and practices. These tools are used without the need to run the actual program. And also importantly, and perhaps even more importantly, they can be included in your automated build and deployment chains, so you don't have to think about running them each time you build the product. But I will touch on that a little bit later. Sometimes people wonder if there's a difference between linting and static analysis tools. In fact, static analysis is a wider term and includes tools like linting, but also other forms of code checks. For instance, checking the test coverage of your code or code dependencies. But I digress. So let's get back to Lint and how to ensure a consistent coding style across your program. For Python, one such tool is PyLint. And for those of you who took part in the interactive session with Jeremy and Steve, you will have had a chance to play with that during the exercises. The homepage of PyLint tells you how to install it on your operating system. As I'm using a Mac, for me this is simply doing pip install PyLint on the command line. FreeBSD and Linux versions may have different commands. Usually, you don't start defining code styles from scratch. Each of these tools come with default settings. After all, Python and other languages have been around for a while, which means that a number of engineers have thought about styling conventions already well before us. One such convention is the Python Enhancement Proposals number 8, or PEP8 for short, and it is often used as a reference point for styling your Python code. And a lot of it is embedded in the default settings of PyLint and other tools. If you're still hunting for more guides, take a look at the Google Python Style Guide, for instance, which also has downloadable configuration files. But if you do find you need to define your own styling, you can do so by adding configuration files to your PyLint or Flake 8 linting tool. In the case of PyLint, for instance, configurations can be specified using a configuration file called .pylintrc. If none is found, the internal default settings will be taken. Finding code that deviates from your coding style is one thing, but doing the formatting is another. Wouldn't it be great if we had a tool for that as well, an auto-formatter, say? Well, you're in luck, because for Python such a tool exists, and it is called black, as the color. So you can now check and correct your code for inconsistency all in one go. Which brings me to how our team employed static analysis in a project we've been working on for several years. To set the scene, let me give you a quick run through the application. It's an app used for medical image analysis and effectively a data pipeline between images sent from a medical scanner at one end and a standalone medical image analysis tool at the other. The project consists of a set of Python applications run in Docker containers, linked together through an event bus, also written in Python. To ensure coding style consistency, we use a Python tool called Flake8, and for formatting we use Black, which I just mentioned. I'd be going into too many details to explain how we configured Flake8 and Black. What I do want to focus on is how we integrated both in our development and deployment process. And for that I need to explain how we set ourselves up for code deployment in a bit more detail. It may sound like a digression, but it all hangs together in the end, so bear with me, I will try to be as brief as possible. The GitHub repository for our source code is organized into a release and an integration branch. To work on a feature, an engineer would branch from integration, and when finished create a pull request to merge back into the integration branch. When the code is ready for release, the integration branch will be merged into the release branch with a tag marking the release version. For automated deployment, we use GitHub Actions. Each time a developer creates a pull request to have the changes merged into the integration branch, GitHub Actions will trigger all tests to run. Now the question is, can we use GitHub Actions to perform a static code analysis? Can we integrate it with our existing workflow to perform unit tests, linting and auto-formatting all in one? And indeed we can. In fact, we went a little bit further and mandated a code auto-formatting and linting for any commits to any branches at any time. Explaining how to set up GitHub Actions is beyond the scope of this episode. Suffice to say that you can configure a workflow in YAML format, and it is in there that you can implement and specify the use of Flake8, Black or Pylint. In our case, however, the setup was further simplified by using yet another tool called pre-commit. Pre-commit allows us to perform other linting and formatting on, for instance, Docker configuration files, etc. It nicely bundles together all the static analysis tools we use, including of course the ones for Python. Pre-commit is a tool that is based on so-called hook scripts in Git. Like GitHub Action workflows, pre-commit is configured with a YAML file in the project's root folder. With pre-commit, we can create a GitHub Actions workflow that performs static code analysis for each commit. This prevents fluff from entering the code line. You can also use pre-commit as a command line tool on your local computer. And in fact, I prefer to do it that way. Pre-commit can be installed locally from the command line with the pip, conda or brew installation tools. After installation, and using the same configuration YAML file from the repository, simply type in pre-commit install, and from that moment onwards, the checks will run each time you locally commit your code. Well, that's a lot of details, and as I mentioned before, you will find a number of links in the episode if you wish to dig deeper, which I hope you will do. What I do hope you will take away from this short episode is this. Don't let your code turn into a pile of spaghetti. Get some static code analysis tools. Both Pylint and Flake are great for Python. Black is also great for formatting. Default settings of these tools are probably enough to get you started, so don't get too hung up over the exact configuration before you start. Think about integrating it into your build and deployment workflow. If you can run unit tests automatically, so why not run the linting and formatting in there as well? It'll save you a lot of time in the end. I wouldn't want to end this episode without sounding a note of caution, however. Unit tests, linting and related tools are not only great but pretty much standard in today's software engineering practices. However, sometimes Pylint and Flake8 appear too pedantic or show too many false positives, to put it differently. Sometimes they may be too lax for your liking, in which case you may wish to fine-tune and adjust the configuration for each. But ultimately, let's not forget that these are just tools that should help you write more robust code, but they do not replace solid engineering skills and practices such as code reviews. And with that in mind, happy linting! Thank you for listening to this episode of Code for Thought Byte-sized. The content and the interactive Byte-sized RSE sessions are created and run by Jeremy Cohen from Imperial College London and Steve Kraut from Southampton University. The podcast episodes are produced by Peter Schmidt. Finally, we'd like to thank UNIVERSE-HPC for their continuous support. And with that, goodbye.